We cover ethers and epoxides in the same chapter, and we previously talked about the reactions of ethers, and it was a relatively short list of reactions that ethers undergo. Epoxides, on the other hand, despite having a carbon-oxygen-carbon bond analogous to an ether, epoxides are much more reactive than ethers. The origin of that additional reactivity of epoxides relative to ethers derives from the fact that epoxides have a very strained three-membered ring where we have sp3 hybridized atoms within this ring that would very much prefer an ideal bond angle of 109.5 degrees, but instead they're restricted into this 60-degree bond angle. And so as a result, epoxides are much more reactive than ethers. And the main type of reaction that we're going to see for epoxides is that epoxides react to release that ring strain that they are undergoing. And so the majority of reactions of ethers in general, and all of the reactions that we're going to talk about for purposes of this class, involve opening up the epoxide ring. And those reactions are generally energetically favorable because of the fact that they are going to release the angle strain, also known as the ring strain, due to the atoms being locked into that non-desirable configuration. So in this particular video, we are going to focus on situations where the epoxide is reacting in an acidic environment. We call this our acid-catalyzed scenario, to open up the epoxide ring. In the next video, we will focus instead on what happens when the epoxide is in a basic environment. Both acidic environments and basic environments will lead to epoxide ring opening. The mechanisms and details of the reactions, though, will be different, and so that's why we put it into two separate segments here. So here we're focusing on situations where the epoxide is present in an acidic environment, and the acid is going to act as a catalyst for opening up the ring. So we're going to take a look here at acid-catalyzed epoxide ring opening. And what I will warn you about or tell you about straight away here is that in this video, we are not going to go through every single scenario that you could see in terms of the types of reactants that will be present. Instead, what you would need to do is look at a reaction, recognize there's an epoxide there, and then analyze it to determine whether the environment is acidic or basic, and go down the appropriate type of reaction pathway accordingly. So what will happen in the case of an epoxide ring opening reaction in acid in general, and then we'll get into the specific details, is that you will have the epoxide, and I'm not even going to bother writing R groups in here at the ends. I'm just going to plug in some lines there to indicate the 4 bonds to the epoxide carbons. And the epoxide will be present with an acid, which could just be simply written as H+, or it could be dilute sulfuric acid or a variety of others. And additionally, in that reaction mixture would be a nucleophile. And this is generally a neutral nucleophile. So it's not going to be an anionic nucleophile because the anionic nucleophile would quickly react with the acid and be no more. So it's going to be a neutral nucleophile reacting in the presence of acid with our epoxide. Some common neutral nucleophiles include water. Remember that a nucleophile just needs to have a lone pair of electrons or pi bonds that are available to come in and attack an electrophilic carbon. So water definitely qualifies because it is neutral and it has lone pairs of electrons. Similarly, alcohols are excellent nucleophiles. For example, methanol or ethanol are candidates there. Thiols, where we have R group directly bonded to SH, since OH and SH are in the same column of the periodic table, alcohols and thiols behave analogously when we're thinking about how they'll act in an acid-catalyzed ring opening. What you're not going to see as a nucleophile here is you're not going to see things where we have a metal such as sodium bonded to non-metal atoms such as oxygen and so on. And the reason why you won't see that here is in this case when you have sodium directly bonded to an oxygen, that would be an anionic nucleophile, and that is a no-go because that anionic nucleophile is a base that would react super quick with the acid to neutralize, and therefore the reaction would not go onward. And so we absolutely, if thinking about how to set up this reaction, got to have an acid present. There's a lot of flexibility there about what acid, and a neutral nucleophile. I've listed a few possible examples up here, but you need to be able to critically analyze a reaction based on what information you're given about it and look at it and say, okay, there's no anions here and there's acid, therefore it is an acid catalyzed scenario. So what's going to happen in the situation where we have an acid catalyzed scenario is that ultimately the nucleophile is going to attack the more alkyl substituted carbon of the epoxide. So it's going to attack the more alkyl substituted. You could think of that as being the more sterically hindered carbon in general. So it's going to attack the more alkyl substituted carbon of the epoxide to form a new carbon nucleophile bond. So that carbon that's being attacked we would describe as the electrophilic carbon. When we think about which of the two carbons of the epoxide is going to be targeted for attack, the one on the left versus the one on the right, under acidic conditions, the nucleophile is going to go to the one that is more alkyl substituted, that is more sterically hindered. So when we say more alkyl substituted, the other way we could look at that and think about that is that a tertiary carbon is going to be preferred over a secondary carbon, which is going to be preferred over a primary carbon. That is going to be the order in which the nucleophile will prefer the carbon of the epoxide. So based on these criteria and the fact that the nucleophile is going to attack the more alkyl substituted carbon to form a new carbon nucleophile bond and open up the ring as a result of that to release that ring strain. And so as a result of this reaction, once the nucleophile forms a bond to one of the two carbons of the epoxide group, that epoxide ring will also have opened up so that you will no longer have the epoxide ring present, and that's going to release the ring strain. So let's take a look at a specific example to go through the mechanism for this reaction. So we'll go through this mechanism for our epoxide reacting with sulfuric acid and methanol. We recognize that these reaction conditions are acidic because clearly there is an acid, sulfuric acid, present within the reaction mixture. When you see an acid reacting, the first thing to always think about is protonation of the organic molecule. And that is exactly what we are going to do here. In the very first step of the mechanism, the fact that sulfuric acid is a relatively reactive acid means that very quickly the epoxide via the lone pairs of electrons on the oxygen are going to act as a base and attack the proton from the sulfuric acid. And I'm going to abbreviate the sulfuric acid just as H+. You don't have to write out the full structure of sulfuric acid every time. You're welcome to take this shortcut. So the lone pair electrons on the oxygen come over, pick up a proton from the acid during this protonation step to give our intermediate here, where our oxygen atom will now have just one set of lone pair electrons, bond to the proton, and a positive formal charge as a result. We will also have bonded to the other carbon of the epoxide an ethyl group and a methyl group. Step 2 of the reaction mechanism. I'm going to go ahead and redraw my organic intermediate. Draw my branches coming off of the epoxide group, like so. Put in my positive formal charge. And from here, what we have to think about is what's going to happen next. At this step, this is where the nucleophile is going to attack the more alkyl substituted carbon. And so we can show that happening by having our methanol, which will act as our nucleophile because it is a source of lone pair electrons or pi bonds, enabling it to serve as a nucleophile in this reaction, comes in and attacking the more alkyl substituted carbon means it's going to attack the one on the right here, so I show that bond forming. In order for that bond to form, the bond between the oxygen and carbon has to break to avoid going over the octet, and the electrons from that bond go on to the oxygen. So we'll go ahead and draw out what would result from that. So I sketch in my methyl group that was right here. Go ahead and draw in the OH group. That OH group originated because we had our epoxide ring. The epoxide ring broke. The electrons from breaking that bond that I'm highlighting in red went onto the oxygen, and the oxygen remained tethered to this carbon right here, and that's the carbon that I'm highlighting on the product side now as well. Then coming along, we come to the next position, and it is at this position where we will create the bond to our methanol. And so we'll go ahead and plug in our bond to methanol here. Plugging in our bond to methanol, there's a proton there that confers a positive charge on that. So I'll go ahead and plug that in. And then our methyl group and ethyl group get plugged in there as well. So this may seem a little bit odd to you as we look at this, because you may be asking yourself, why is it the case that the nucleophile is attacking the more sterically hindered of the two carbon atoms? Why would it go after, under these acidic conditions, the carbon atom on the right rather than the less sterically hindered one on the left? And the reason why it attacks the more alkyl substituted carbon is you could think of this scenario under acidic conditions as being one where there's almost the formation of a carbocation here, making this behave somewhat like an SN1 reaction, where in SN1 reaction, a carbocation forms to make the more stable carbocation, where tertiary carbocations are more stable than secondary, more stable than primary. And so the nucleophile then comes into the more alkyl substituted carbon because that's where the carbocation formed. So we can think of this as behaving sort of like a hybrid between SN1 and SN2, where it takes on some of the characteristics of SN1, that is that the nucleophile comes in and attacks at the more alkyl substituted carbon, much like if there were a carbocation forming. But on the other hand, the other observation that can be made is like SN2, there is an inversion of configuration when that attack occurs. So this particular mechanism under acidic conditions, the epoxide ring opening, is very much like a hybrid of an SN2 reaction due to the inversion of configuration that's observed, and SN1 due to the fact that the nucleophile attacks the more alkyl substituted carbon. So it's really, you could think of it as kind of a hybrid mechanism where it's exhibiting some traits of the SN2, which would indicate, like I've shown here, that the nucleophile is coming in and attacking from the less sterically hindered face of the molecule at the same time the leaving group is leaving. Whereas the fact that the nucleophile is attacking the more alkyl substituted position makes it play out kind of like an SN1 situation. But these are the observations that we can make, and what you need to keep in mind when you are writing out the products for these reactions. If it's under acidic conditions, always have the nucleophile attack at the more alkyl substituted carbon, like we've done right here, highlighted in blue. Also, invert the configuration. So how do we go about inverting the configuration here? Well, one way that we can invert the configuration is just our branches here were a dash to the methyl group and a wedge to the ethyl group. We can make it inverted by making a wedge to the methyl group and a dash to the ethyl group. That's perhaps the easiest strategy for doing this, but whatever you've done, if you assign the configuration as RRS to start with, and then for this final scenario, you would find that the configuration has inverted, that it is flipped. So now we are here at the end of step 2, and I will go ahead and label step 2 as the step where the nucleophile attacks the epoxide, specifically the epoxide electrophilic carbon, at the more alkyl substituted carbon. And I'm putting this down specifically because this is super important since it is specific to the acidic conditions. When we jump into reactions in basic conditions, we're going to see the regioselectivity is different, that the attack is not at the more alkyl substituted carbon, but instead it's at the less alkyl substituted carbon. So I will also add this little annotation here to remind you that due to the fact that the attack is at specifically this more alkyl substituted carbon and not randomly at both carbons, it does imply that the reaction is regioselective because it's going to make a specific constitutional isomer rather than making a random mixture of different possibilities that would correspond to the attack of the nucleophile on either of the two epoxide carbons. Instead, it has a preference for just the more substituted one, making it fit this definition of regioselective. Selective meaning it has a preference for a specific constitutional isomer over others. So we are almost to the end of this mechanism, but we do have one more bit to fill in here. And so I'm going to zoom out so that we are able to take a closer look at that last step. Onward to the last step of the mechanism. As is common when you create an intermediate that has a protonated oxygen and a positive charge, deprotonation is a common step to alleviate that situation. And that's exactly what we're going to do here. And this is exactly why the acid is described as a catalyst for this reaction, because the catalyst is consumed during the protonation step and then regenerated during the deprotonation step at the end. So let's go ahead and draw out our intermediate, like so. Put my positive charge on there, keeping everything going along here. So I just redrew my structure from above. I did rotate it around so that it looks a little more geometrically pleasing. But the way that we know that it's still exactly the same structure is if we assigned the configuration to the structure up top here, we would find that that configuration is R. The same is true down here, that this is also R. So that's how we know that those two structures are identical. And then the deprotonation step we show by bringing in some source of lone pair electrons to grab that proton from the acid. I'm just going to use another unit of methanol for this. And that methanol can come in using its lone pair of electrons, grabs a proton from the acid. That forces the oxygen-hydrogen bond to break, and that is going to give us, as a result, our final product here. And in our final product, I'll put in my methoxy group, plug in my methyl group and ethyl group, making sure I make those wedges and dashes the same as they were before to illustrate the reaction is stereoselective. And I'll go ahead and circle the final product. And I'm also going to explicitly write out my designation here that the reaction is stereoselective. It is stereoselective because we are creating or manipulating a chiral center. That's the chiral center that I put in the yellow star in the lower right-hand corner here. And during the course of the reaction, the configuration of that chiral center is not randomized. Instead, it has a specific preferred orientation. That preferred orientation is due to the fact that the nucleophile attacks from the more sterically hindered side of the molecule. So with this information now in mind, you should be comfortable with going through the steps of an acid-catalyzed ring opening reaction for epoxides by evaluating to identify what the nucleophile is in the reaction mechanism, having that nucleophile attack the more alkyl substituted carbon of the epoxide with an inversion of configuration, making this mechanism fit some of the characteristics of SN1 and SN2, giving it attributes of both of those types of mechanisms. You should also be comfortable, in addition to writing out the mechanism for this, if I give you reactants, to tell me what the products of those reactions would be, including the stereochemistry.